There's Banff proposals, and you get more details about volumes, planned volumes, and all of that. So this is advertising. Also, there are, as my understanding says, there are other simplifications, say p-local finite groups, the theory of these. Aschbacher, Chermak, Bob Oliver, and many others are working on it, which is, I think, very important because that's a separate area of mathematics which covers large part of the classification. That has always been a little bit of a problem, as my understanding is, that much of the classification proof just did as much as was required, and this puts a large part in context. There's an independent thing, the amalgam applications of the amalgam method by Meyer, Frankenfeld, Schroth, Stellmacher, and a very recent edition by Paul Flavel, who didn't appear. You can find in the archive a series of papers which gives a much better, apparently much nicer proof of a cornerstone of the classification called the signalizer functor theorem. So there are developments. That's what people would ask. Don't ask me about details for sure. But these are the names. Okay, you have heard of the GI problem before, I believe. But, okay, so decide fast if two n-vertex graphs are isomorphic. And as Babay proved about a year ago, there is a quasi-polynomial algorithm. And basically, he solves a group theoretic problem, the string isomorphism problem. So it's the right kind of generality, apparently, which you have probably heard before. But just to repeat, if you have two strings, x and y, which are colorings of the alphabet of n elements, then decide whether they can be brought into one another by an element of a group G, which is actually given by generators. So it's a permutation group theoretic problem which generalizes the graph isomorphism problem, and graph isomorphism doesn't appear anymore. But if you were here before, then you have heard a lot. And this is what Babay solves in quasi-polynomial time. Okay. Let me go to consequences of the classification. Okay, as Lottie said, there's soft ways of using the classification, means that other people did the hard work. They put together wonderful compact theorems, and we are using them instead of doing the work ourselves. Okay, so one example is that Lottie also mentioned, Schreyer's hypothesis. That's still called a hypothesis, even though it's proved that the outer automorphism group of a simple group, so out L divided by L, is soluble. That's what Lottie uses. Another, which is a favorite of mine, when people ask me the question, okay, can you avoid the classification and other problems? Okay, here's a challenge. There are at most two simple groups of the same order. Try to prove any sensible estimate without the classification, and I will be very glad to. I would even read your paper. Okay. Unless it's more than 100 pages. Okay. Anyway, another lovely consequence is that all doubly transitive groups are known. This kind of problem goes back to Jordan, which are doubly transitive groups, and the neat consequence is that all 6 transitive groups are either alternating or SN. They are giants, as Lottie calls them. Let me mention a major open problem in elementary proofs. Prove that there are only 10,000 transitive, 1,000 transitive groups, are either alternating or SN without the classification. I think it's not a problem for me. I think Udi Hrushevsky sometimes wonders about it, but you should ask him. But this is something that one could perhaps wonder about. It's a good direction. So something that's related a little bit to that is old work of mine that seems to have some consequences, more recent consequences. So let me list some by a biased account of some elementary quasi-polynomial bounds for permutation groups. So László has a big paper on estimating the orders of doubly transitive groups, and I could add a lemma which simplified the proof and improve the bound. So I can prove that the orders of doubly transitive groups are quasi-polynomial, n to the log n squared. Actual truth is you should be able to chop off these two, but the method probably does not allow for that, or the group contains an. So that's an old result of mine, but it was pretty useful, as you will see in the long run. So I had an elementary proof of that. So very recently I found an extension. So doubly transitive means that, in a way, that you fix one point and you just have one orbit remaining. What if you have two? That's called rank 3 permutation groups. And I could prove a similar quasi-polynomial bound for the orders of these in 2015. There's the recurring comment that it's based on Babai's work. Actually, 3 different little papers of Babai, and I'm putting together, and I'm getting by a short argument. But it tells me at least that maybe one can go on in this direction. It's a little bit the results of Sohn and Wilms that Babai mentioned on the bounding the order of primitive but not doubly transitive groups is also in this direction. So the dream would be to get some version of Cameron's theorem which classifies large primitive groups. So these one could view this result, this little result, and the major result of Sohn and Wilms as steps in this direction. But there's an awful lot to go. Okay, here again we have exceptions. So either the group is small or there are some known exceptions. Okay, so here's a comment. Why is it used? Why do you want to avoid classification? It's done. Okay. One thing, it's pleasing to have a proof that you understand. But there is a more recent development. Helfgott and Seres proved a famous result that the diameter of the alternating group is quasi-polynomial. So meaning you take any Cayley graph of the alternating group, then it's quasi-polynomial. It's a ancient, maybe folklore conjecture that it should be polynomial. And the proof in an essential way uses a lemma of Babai and a lemma of mine, but it's like they blow it up, they prove approximate versions and build on some extra amazing structure. But sorry, but it seems that maybe without this doubly transitive argument, this proof would not exist. Okay, Helfgott is clever enough, he could have found it for himself, but still, it's an extra argument for classification-free proofs. Here's a problem that in a hidden way still Helfgott and Seres use the classification theorem via a lemma of Babai and Lemma and Seres that they use. The question is whether it's necessary. I'm sort of working on this issue. I should even mention that working on this gave me a hint for a lemma which I could by accident use half a year later to do what I'm trying to talk about today. So it turned out to be very useful, at least for me. Some people who help people writing proposals, they say it's synergy, whatever it means. Okay. Okay. Actually, there is some progress on this work. There is an abstract by Harald Helfgott in the Groups and Actions conference. We are aiming at better bounds, shorter proofs. It's work in progress. Okay, it's not even yet decided what any papers will contain. There is some, what I'm trying to say, there is some progress. So maybe the advice is, if you can wait, don't read Helfgott Cheresh, because there will be a shorter proof. Okay. I may be moving too fast, but still, there'll be a long break anyway. So, so what I'm trying to advertise today is that there is a key lemma of Babai's GI paper that you have heard before, which I simplified in a nasty way, that if you have a primitive permutation group of degree n, and it has an alternating quotient of something like log n squared degree, then the group itself is isomorphic to the alternating degree group of degree k. So the proof of this uses the classification in a soft way through Scheyer's hypothesis, and as László kindly explained, replacing just this lemma is enough to get a quasi-polynomial bound for the graph isomorphism problem. Okay, I should, okay, then I made even, okay, it's 2 or 8, the maximum of 8. Okay, I made a mistake, so, yeah, sorry, so I made a mistake. Okay, that happens. Okay, I will try, but I'm not sure I can find. No, anyway, 2 is. Okay, well. I put it here. Okay, so it's roughly log n, and what I can prove by an elementary argument, which it could be written up in probably from 0 in 10 pages, that the same holds with k for k greater than log n to the 5 or 6 or something. I don't care about it. And this is based on what I call a weird lemma that I proved. So let me state the weird lemma and say how you can use this. So you really have to consider something very silly. You want to prove something about primitive groups. You can't use induction, go to transitive. So you want to prove something about transitive groups. Not so good, you have to consider stabilizers in transitive groups. This seems to be a very strange class of groups, but actually there is a little result of Isaac's, which is a combinatorial flavored result, which is about this class of groups, which was sort of gave me a hint of that this is this interesting class of groups that you may prove something about. So what do I want to bound? I want to count the number of isomorphism types of abelian composition factors of G. So again, I'm considering transitive permutation groups and point stabilizers in them. And I want to prove that these things I count, they're at most log n squared of them. Okay, so one is somehow really forced to consider this. One has a hint of so you have to find the statement. That's the most difficult part. Once you find the statement, there is a relatively short inductive proof, but that's the main thing. This implies immediately, it's a very easy, trivial argument, that the total number of abelian composition factors of transitive groups is also bounded by log n squared. But the proof has to go through considering stabilizers. Okay, so I have a statement of the weird lemma. So how do we use this? Okay. So we have a logarithmic, polylogarithmic bound for the number of abelian composition factors of transitive groups. Now, if P is a primitive subgroup of Sn, and we have a normal subgroup K such that the quotient is AK, where K is at least log n to the sixth, then note first that K is transitive. Any normal subgroup of a primitive group is transitive. A trivial argument shows that P over K, which is an alternating group, has a large cyclic group, large in the sense that the product of that it's the product of log 2 log n squared CP subgroups. It's trivial number theory that tells you that. And now all we do is take the inverse image of this subgroup. So we have K, on top we have C. This is a transitive group. K is transitive indeed. And it has too many abelian composition factors. It contradicts the weird lemma. So that's how the weird lemma is being used. Okay, just a little hint of the proof, not the actual proof, but I like to prove baby versions. So let's, a previous work with Alex, it did prove very useful to prove a baby version of a theorem we wanted to prove and then do the general case. But a sort of baby version of this is something I found earlier that it's much, much easier, but it gives a hope that something like this might work. So consider, again, a transitive group, not stabilizers this time, and assume that AT is not a section quotient of a subgroup of G. This is this Boboy-Cameron-Palfy class that has been mentioned before. Using the classification, we know that such primitive groups have polynomial size. But we are transitive now, and what we can prove, in this case, by a rather short argument, in some sense, that the product of all the different prime divisors that are at least T is quasi-polynomial. So it's not composition factors all, but all, and not stabilizers, but the transitive groups themselves. Now the proof uses the ancient doubly transitive group of mine. This is the basic case, and there is this very simple induction that reduces everything to this basic case, which uses a lemma of Jordan, which is basically my final word on this proof. So the lemma, very classical lemma of Jordan, says is that if you have a primitive group and Gx is a point stabilizer, and delta is a non-trivial orbit of Gx, then if P divides Gx, then it divides the order of the action of Gx on delta. So this can be used to set up a very simple induction argument, and the only cases where you cannot handle are the doubly transitive groups, which I have done long ago. Okay, so this is a quasi-polynomial bound for something like the exponent of the group, and that again was a hint that something like that may happen. In the proof of the weird lemma, this has to be replaced by a lemma of Wieland, which actually appears in a paper of Higman, but luckily this paper of Higman and the lemma is mentioned in an ancient survey of Cameron. So it was not so easy to find, but I was very lucky that I put it away like 20 years ago. So Cameron had the taste to choose to put it in his survey. Okay.
What do you mean by the order of the action?
Well, there is an orbit of Gx. There is an action. It has an order. I mean the faithful part. Okay. Yeah. Okay. So for the rest, see the archive. It has been there for a while, and a number of people have looked at my argument. Okay. So this is. Okay. So now I will go to a completely different thing. Forget about permutation groups for a moment, and talk about some joint work with Alex. So there's a different type of example of avoiding the classification theorem. So consider SL2Z and try to count the number of congruent subgroups of a given index, well, given in the index at most n. You can do actually this, try to do the same for SL and Z for n larger. And with Dorian, Goldfeld, and Alex, we proved the result which I think surprised us, that somehow there is an expression which is controlled by a constant, and the constant can be determined exactly 3 minus 2 times square root of 2 by 4. So there's a magic number. Why should such a thing exist? Okay, it relies on Bombieri, Vinogradov, and some tricky elementary arguments and all that. So this is an old result. And another old result is an extension by Lubotsky and Nikolov to SL and Z, where the magic constant becomes this thing I will not attempt to read now. But there is an explicit constant. There is an extension to arbitrary arithmetic groups, but let's just mention this. Now, the original proof did use the fact that we know the subgroups of PSL2Q or P. It's very explicit. In general, we don't know the subgroups. It's impossible. But there is an asymptotic structure theorem on subgroups of SL and Q by Larsen and Pink, which for Q prime was first proved by Nori. And this can be used to replace. Okay? So the Lubotsky-Nikolov result is classification free because of this structure theorem of Larsen and Pink. So this is a major tool, which I now will. Well, I think it will be a very short talk, but still, I will make it more explicit. So Larsen and Pink proved a structure theorem, which has the best is to state the main corollary, which is in some sense equivalent to the main statement. So take any linear group, think of n as being bounded. Okay, n is small; it doesn't matter, and take any composition factor simple composition factor of such a linear group. Then L is known. It is on the list that I showed you before, or L is less than f of n. I think it's not explicit. In reality, this theorem was known before. It was a theorem of Weisfeiler that's based on the classification. And there the function is something like n factorial. But the main point is that the proof of this is completely elementary. So this statement, the same thing, follows for all finite quotients of SL and Z. Therefore, if you want to do anything about, okay, so yeah, there are congruence quotients for n at least 3. So if you want to do anything subgroup counting, then unless you are very unlucky or want some very, very precise result, then you can use Larsen Pink to make your arguments classification free. So, and this is one example. There are many other examples. So this is a major breakthrough, I think, in classification free proofs. But I just wanted to list this one. Let me have the personal note that so I think I met Alex first in Oberwolfach. I gave a talk on my then favorite subject, group enumeration, and somebody whom I didn't know came up to me and was talking about something I didn't understand. Congruent subgroups and pro-P groups and stuff like that, which I didn't learn at the time, and it took me about a year to learn. And maybe these papers are the proof that I at least did put some work in it. Also, Alex explained some of this stuff later. But at first, it didn't make sense to me, I have to admit. Well, okay, so let me go to the big problem, the biggest problem in the area. Is there an elementary proof of CLFSG that would be that there are finitely many sporadic groups. Is there an elementary proof? Some comments maybe can be found in some papers of Udi Hrušovský. So this would not be my target because it's sort of too big. But somehow this is would be the dream of this area, and in a sense one could view the Larsen-Pink theorem as a step in this direction. So proving that there are finitely many sporadic groups of bounded dimension. Okay, so I think that's really all I wanted to say.